This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club seminar series. This is session number 197. I hope everybody's summer is off to a great start and you're staying cool. The title of today's presentation is GLM Background in Data Quality Product Imagery for Operations. I'm pleased to have Eric Bruning from Texas Tech and Joseph Patton from Success with us today. Following their presentation, we'll have a discussion facilitated by Carl Jones, meteorologist and satellite focal point at the Weather Forecast Office in Grand Forks, North Dakota. Glad to have everybody with us today. Just a few reminders before we get started. As you just heard, this session is being recorded. We encourage everybody to mute their microphones and turn off your webcams for the recording. Upon the start of the Q&A, which will occur after the presentation, I would encourage attendees to post their questions in the chat, and we'll field them in the order they are asked. Of course, at that time, if you'd like to ask a question using your microphone, you can do so. If you have not signed in with your full name, please specify your name when asking a question in the chat so we can follow up if necessary. We're always looking for future presenters for the Satellite Book Club. There's a link in the chat if you would like to present. Maybe you have a presentation from a past or upcoming AMS or NWA meeting. It doesn't have to be satellite at its core, but it should have some satellite use incorporated into it. The training team can help create training materials that may be unavailable or point you to materials you may be unaware of. Ross Van Til with the Office of the Chief Learning Officer can help with that. I'd like to thank the OCLO, the GOES Orange APSS programs, and our presenter, facilitator, and all of you for being with us today. All right, moving on to our introductions. Eric Bruning is a professor of atmospheric science at Texas Tech University, where he specializes in meteorology of thunderstorm, electricity, and lightning. He designed and implemented the operational GLM gridded products and serves as the GOES GLM and MTG Lightning Imager science teams. Joseph Patton is a faculty research assistant at the Cooperative Institute for Satellite and Earth System Studies at the University of Maryland, College Park. His work focuses on creating training materials and conducting outreach for the GLM on board the GOES-R series satellites. He previously served as a meteorologist at the Weather Forecast Office in Goodland, Kansas. Eric and Joseph, welcome and welcome back to the Satellite Book Club.
Thanks, Jordan. I think I have the first slide here. This is Eric. And yeah, Joseph, I believe I've got the next slide after our intro here. Anything you wanted to say to set us up?
I just want to say thank you, Jordan, for that introduction. A little taste of what we're going to be talking about there is in the imagery in the top left. And I think we're ready to get started. So go ahead, Eric.
All right, thanks. Next slide, please. All right, so before I introduce our effort on the GLM background and data quality products themselves, I wanted to start with a reminder of the principle of operation of the Geostationary Lightning Mapper. It's a 500 frame per second event detection camera in geostationary orbit, and it operates in a 1 nanometer wide band at 0.777 microns, so it's in the near IR band, focused on an oxygen emission line in the spectra. So the GLM is really just a very fancy digital camera up there in space, and it is continuously collecting photons, and then in every one of the 2 millisecond frames, it's gathering those photons up, and as the instrument operates, it tracks the background brightness, and then any pixels that receive additional photons that are in excess of some threshold, that results in lightning events. And so you can see that in the upper right corner in this figure from the GOES data book. The blue dots are the actual values sampled by the instrument at each frame in the pixel being illustrated here. There's a running average that's maintained, that's the blue line for the background brightness value. And then based on that background brightness value, there's a detection threshold that's set at some level above that background. And any pixels in any 2 millisecond frame that exceed that detection threshold result in one of these triggered events, which is then a candidate lightning event. So you can see the blue dot in the top center of this panel that is one of those lightning events that was actually observed above the red detection threshold in that particular frame. Okay, so we've got an image that's constantly maintained, that's being collected by the CCD in this near infrared band, and that's what we're going to rely on for the rest of this talk to both characterize the background and the data quality as well. So next slide. All right, a little bit more about the GLM focal plane array, because this does actually play into some of the features that we see in the data quality product and in the backgrounds. The GLM focal plane is a charge coupled device sensor that's read out in 56 subarrays. So again, a figure from the GOES data book on the left-hand side. You can see each of these 56 subarrays overlaid on the nominal GOES East field of view. And each one of those has separate readout electronics associated with each of those subarrays. And on the boundaries of those subarrays, for some hardware and electronics reasons, the sensor is more sensitive on those subarray boundaries. And so you can see that in this raw background image here. It's actually been navigated into the geostationary fixed grid coordinates. But it's a fairly raw image. And you can see, for instance, over South America, that there's these brighter bands, and also that each subarray has a characteristic sensitivity level in terms of how much it picks up photons. So all of that can be calibrated out into the backgrounds, but because of that extra sensitivity on those subarray boundaries, that influences as well the sensitivity to lightning there in a couple subtle ways. All right, I will say next slide. All right, so here's how we process the data in order to generate a data quality product and this background image. So in the upper left corner, we start with a background image. This actually starts out as a full 14 bits of sensitivity, so that's about 16,000 different grayscale levels. And if we follow the arrow across the top path there, we can take that background image, calibrate it to radiance. I haven't shown that process here, but we did that in operations for the test bed in the third week of the trials. And Joseph will show some of those results, I believe, later on. But after we do that calibration to radiance, and after we navigate that image, it basically serves as another image of the geostationary full disk that updates every 2.5 minutes in a near infrared band. And so you can see what that looks like here in this test data before calibration. It's already been navigated here as well, and you can see the geostationary field of view. For operations, because we're trying to be cognizant of bandwidth limitations, we also reduce that to 16 gray levels so that the data files take up less space. That's totally a decision under our control, and we could do whatever whatever an end user might want there, up to 16,000 levels. All right, so that's the background image that we can produce every 2.5 minutes. Then moving to the next arrow, the background also implies a minimum detectable event energy at each pixel. So the threshold is set based on the background brightness, and based on calibration, we can also say then that given that threshold, GLM is sensitive to lightning events that happen with a certain known energy. And so based on calibration to other space-based sensors like the lightning imaging sensor dataset from the TRIM mission and from lightning mapping arrays, ground-based radio measurement systems, we can calibrate a flash detection efficiency. And so you see that in the lower right-hand corner here in blues and greens. We basically get a percentage between 0 and 100% of how many lightning discharges we expect to see. As you go towards the upper left corner of the image, you notice this fall off towards bluer colors, which are lower detection efficiencies. That's a systematic known offset that GLM has. Also, you can see the subarray boundaries as these brighter streaks of higher detection efficiency. Again, those pixels are more sensitive. So in most cases, they're going to actually observe or be more sensitive to lightning discharges on those subarray boundaries. However, if the sensor gets completely saturated by photons from a bright cloud top, those pixels can become completely blinded to any extra photons that are caused by things like lightning. And so while those photons are more sensitive in most illumination conditions, in extreme illumination, typically below the satellite subpoint in the tropics and subtropics, those pixels can become saturated, and we can then detect that because we're looking at the background image and say that these certain pixels are likely to be blinded to lightning. And so you see in the inset image, the background flash detection efficiency, the enhanced flash detection efficiency on the subarray boundary, and then these yellow and white pixels are places where we're close to or at the saturation level, and we would expect to see much, much less lightning in those locations. Okay, so we then combine these saturation flags and the flash detection efficiency into a product image. And again, we're reducing it to 16 unique values so that we can keep the file sizes small. So that's the sort of two core products that we created for the Hazardous Weather Testbed this year. And we're extremely indebted to Philip Bitzer at the University of Alabama in Huntsville, who did a lot of work to work around some unavailable information in the original GOES GLM product design stream to navigate and calibrate these background images and do the threshold conversion we need for flash detection efficiency. So we really rely a lot on his code for making this happen in real time. All right, so next slide. And this is, I believe, my last slide here. I just wanted to emphasize one more time, these subarray boundaries were something that a lot of the forecasters weren't aware existed because it is kind of a low-level instrument detail. So that was one of the positive outcomes this year, is getting to explain a little bit more about the sensor to our operational users. And again, I want to emphasize that most of the time the subarray pixels are more sensitive, but then they get blinded. And instead of being maybe 10% more sensitive to lightning, they become almost 100% less sensitive to lightning. And so that's the essential thing we're conveying in the product here. If you're an astute observer of my color bar here, you might have also noticed there's a bunch of other flags. All of those are flags that are that we could, if we had complete access to every bit of information in the ground system, we could populate those data quality flags as well. But that sort of requires a kind of major surgery into the ground system algorithms that I don't think is super likely. But we wanted to reserve those spots in the product design to indicate the kinds of things that we could indicate to users, if not in the GLM era, in the GeoXO LMX next generation Lightning Mapper product design, perhaps. So with that, I will stop talking and turn it over to Joseph.
All right, thank you, Eric. Next slide. Okay, so now we're going to shift gears a little bit, and we're going to be talking about what those products that Eric has been describing actually look like in AWIPS, and what some of the forecaster impressions were from trying to use those products in an operational or simulated operational setting. So let's start with the GLM background imagery. That's what's being shown in the top right on the panel on the right-hand side. Mostly there were mixed responses on the utility of GLM background imagery. In an operational setting, one of the things we wanted to see was whether it could serve as a possible substitute for visible imagery from the ABI in case, for whatever reason, the ABI observations were not available. So that comparison to the ABI visible is at the bottom on the right-hand side. Forecasters noted that there were some advantages of using the GLM background imagery. Like Eric described earlier, you get that near full disk coverage that updates every 2.5 minutes, which is about 4 times faster than what you get with the ABI full disk imagery. The varying shading that you can see on the top right-hand side is at the same resolution of the GLM, which is 8 kilometers by 8 kilometers. And that was useful in identifying high, bright cloud tops and anvil shields from convection. So you got the idea of where convection was occurring by using the GLM background imagery. Next slide. With that in mind, some forecasters did find limitations in using that background imagery as a stand-in for possible missing ABI visible radiance imagery. Most of their difficulty stemmed in identifying important convective features, which you would really need a higher resolution in order to be able to determine from that imagery for warning decision making. So some of those examples that a forecaster might look for would be overshooting tops from a strong updraft, or inflow clouds, meaning that you've got strong inflow, moist inflow that can feed on the thunderstorm life cycle. And those are things that you may be able to pick out in the visible imagery on the lower right that are less distinct in the GLM background imagery in the upper right. So in this case, general locations of storms can be determined, but it was really more difficult to ascertain the degree of severity of those storms using just the GLM background imagery. So those little signals that you might look for in the visible imagery were a bit harder to ascertain in that case. Next slide. So now shifting gears to what that GLM data quality product looked like. Like Eric described, it's a real-time detection efficiency, or DE, estimation per pixel based on the ISS or TRML-LIS lightning climatology and current GLM event detection thresholds. You know, if you've got a higher threshold, then you might be detecting less lightning at that particular pixel. The original color scale developed for that data quality product is in the upper right-hand side, and it was tested in AWIPS during the Hazardous Weather Testbed experiment this spring, using various shades of blues and greens to convey the typically increasing detection efficiency of lightning by the GLM towards the center of the field of view of the instrument. So, you know, as you get closer to the subtropics and the tropics, out towards the eastern coast of the US, that would be, you would have a higher detection efficiency for the GOES East or GOES 16 GLM. And then likewise, as you get closer to the tropics on the west coast of the US out towards the Pacific, then you get a better detection efficiency with the GOES West, or currently GOES 18 GLM. And on top of that data quality detection efficiency information, like Eric described, there are a series of data quality flags which are reserved for bits of data that may be able to determine have possibly degraded GLM detection efficiency. So there's a whole list of colors there in the color bar: white, yellow, red, gray, black. And all of those colors pertain to different reasons that, like Eric said, if we had all of the data available to us, that we might be able to make a determination that there would be there might be some sort of issue with that pixel. And some of those things we've talked about, some of those false alarms maybe we've talked about before, like sun glint or solar intrusion. But for this experiment, we're going to be focusing on just the at or near saturation pixels. So those are the white and yellow pixels that you see popping up on the right-hand side. Next slide. So focusing in on what those pixels represent, those were the only two data quality flag pixels which were populated for this hazardous weather testbed experiment. And white corresponds to pixels which are at saturation and therefore cannot detect any more lightning than what was already detected in that time frame for that one particular pixel. And yellow corresponds to pixels which are near saturation. So they're not quite at their upper limit of light that they can detect, the number of photons that they can detect, but they are prone to reaching that level of saturation if they were to detect more light. So those two together can give a forecaster an idea of, oh, there might be some degradation in the quality of GLM flash detection because these pixels are at or near the maximum amount of photons they can detect. Next slide. So one thing that Eric was describing was those subarray boundaries. And as we know, this along the subarray boundaries, the GLM instrument is more sensitive to light. And typically that would mean that you actually have an increase in the number of flashes that are detected. But if the GLM is detecting so much light at those pixels that those individual pixels reach their saturation point, or the maximum number of photons that they can detect, then you're actually going to be at a point where the GLM instrument can no longer detect lightning at that particular area. So these data quality flag pixels show up where the instrument is often more sensitive along the subarray boundaries, and that can mean that it's going to have a lower detection efficiency than it would otherwise. But that does not necessarily mean that no lightning will be detected there. It just means that there could be potentially degraded detection efficiency. You know, if it sees all the photons that are from lightning, and then it receives some additional photons because of the overlapping subarrays there, then it may still be able to accurately display the number of lightning flashes. And conversely, if it's receiving a lot of light from those subarray boundaries, and it also receives a ton of extra lightning, especially during times where there's high bright cloud tops, right? So you've got more light coming to the instrument. That could result in a situation where the GLM would detect less flashes than it would otherwise. Next slide. So now let's go back to what we had before. We've got the GLM data quality product in the top right. That shows us the detection efficiencies in the blues, and it's also got the data quality flagged pixels in the white and yellows, which are at or near saturation. And just based on the data quality flag pixels, that might tell a forecaster, hey, there might be some degraded flash detection efficiency along this, along this known subarray boundary where those data quality flag pixels are present. And if we compare that to what's being observed in the same area by the GLM gridded product of flash extent density, which is in the lower right-hand side, in that red oval is highlighting the overlapping region between the data quality flag pixels and the FED gridded product. We can see that there appears to be a lower number of flashes that are detected by the GLM, and then also there's some signal loss in the spatial extent of lightning as well. So a forecaster might see that as an odd band of missing lightning in an area where they would definitely expect there to be lightning from an ongoing storm. So we can see that that's co-located with an area with pretty high cloud tops, as well as those data quality flag pixels. So this data quality product is really giving forecasters more information to make sense of the GLM data that's in front of them based on what we know about how the GLM detects lightning. Next slide. So now putting it all together, we've talked about the background imagery, we've talked about the data quality product. Well, what would that look like all together? So this here is a 4-panel example of what forecasters were looking at in AWIPS during the Hazardous Weather Testbed experiments earlier this spring. And in the top right, we've got our background imagery. And in the top left, we've got our data quality product. In the bottom left, we have the flash extent density from the GLM and some ABI imagery. And then in the bottom right, we have just regular visible imagery. So next slide. So combining these all into one standard 4-panel product shows that we've got that confluence of high, bright cloud tops that we can see in the visible imagery. We've got increased light detection that we can see in the background imagery from the GLM in the top right. We can see that that's resulting in near or at saturation pixels in the data quality product in the top left, and also possible degraded GLM performance or detection efficiency, which manifests itself in the lower number of flashes observed in flash extent density in the lower left. So that's kind of what it would look like altogether to a forecaster if they were to load one of the standard 4-panel procedures that were tested in AWIPS earlier this year. Next slide. There were also some products that were tested to see how well we can synthesize this information into one quick to understand product that could very quickly give forecasters an idea of just, okay, I want to keep in mind that there might be some degraded quality here. So if I'm looking at the GLM flashes when I'm augmenting my warning decision-making processes, that I understand that there might be some limitations for the GLM depending on what's occurring in what area. So this is an example of what that product might look like in a combined sense. Next slide. So what this product is showing is it's overlaying all this information that we've talked about already. So first of all, I want to talk about the detection efficiency. So if you see those dark red colors in the top left, those are detection efficiencies, estimated detection efficiencies from the GLM, the GOES East GLM, that are less than 40%. So in that case, we can see that the GOES East GLM is going to likely be detecting less than half of the actual flashes present over the Pacific Northwest, for example, which is what we expect, right? That's why forecasters on the West Coast use the GOES West GLM as opposed to the GOES East GLM. But we have basically a transparent detection efficiency, so no shading at all, where the detection efficiency is greater than 40%. So that goes back into the central US and the eastern US, and then out over the Atlantic Ocean too, where the GLM has a lot of operational capabilities, as has been discussed in recent Satellite Book Club talks. So we've got that red shading if it's less than 40%, and totally transparent if it's greater than 40%. And that's being overlaid. The grayscale image you see on the back is the GLM background imagery. And we can see those sort of stripings of the subarray boundaries as they stretch across the United States. And one other thing that I want to take the time to mention here is that the GLM background imagery, the reason why we were comparing it to the visible imagery is that it acts a lot like the ABI visible imagery. You know, the sun is setting in this imagery, so we can see that as the sun sets and there's less light being detected just in general by the GLM, that those that background image darkens, right? Because it's got less sunlight that's being reflected back to the GLM optical sensor. So in that respect, it operates a lot like visible satellite imagery does from the ABI, and it also can explain why we expect higher detection efficiencies from the GLM instruments at night, because we have those much darker backgrounds. The GLM instrument can deploy much more sensitive or lower thresholds for being able to determine if a flash of light met the event criteria that it would determine from that background image. So that kind of ties it all together in terms of how the GLM detects lightning and why it's more efficient at night. But going back to this data quality product, so in this case, instead of having the different colors like white and yellow and all the other different colors for the data quality flags, all the data quality flags are shaded pink. And you can see a little bit of that in the very top left corner, but we're going to get into what that looks like in a zoomed in example here in a second. And then overlaid on top of all of this is the flash extent density, which are those blue and light blue and green colors. So next slide. So this is the same imagery as before, but now we're zoomed in into that southern plains, sort of Texas, Oklahoma, Arkansas, Louisiana region. So this is our GLM background imagery, which is the grayscale. We've got our detection efficiency, which is totally transparent because we're all greater than 40% at this time, at least estimated greater than 40% at this time. The flash extent density is in our blue to red color scale. So we can see that we've got an ongoing complex of storms. We can see that those reds in the center indicate that we've got likely a strong updraft resulting in a large amount of flashes over a small area. And we can also see, based on the GLM background imagery, that there appears to be two subarray boundaries evident by the white striping, one going across the upper third and then one going across the bottom third. And they both go horizontally or near horizontally across Texas in this case. So one thing that I did want to point out is that when you've got that confluence of high bright cloud tops, which are going to be reflecting a lot of light to the GLM instrument, that is where you might find pixels that are going to be at or near saturation. So if you look closely at that bottom subarray boundary, you can see that there are a number of pink pixels showing up, and those pink pixels relate to the at or near saturation pixels that we're seeing in the other imagery. So that is commonly found along or across these subarray boundaries as more light is detected by the GLM instrument. Looking at the flash intensity product in this case, they're not exactly co-located, so we don't see that much of an impact. But as that storm continues to move towards the east or southeast or develop further south, seeing those pink pixels in the GLM data quality product could give forecasters an idea of, okay, I should be prepared to understand that even though the flash counts might be lower in this region, that doesn't necessarily mean the storm is weaker, because the GLM could have this very localized, lesser estimated flash detection efficiency. Next slide. So these, all of these imagery were created by forecasters during the Hazardous Weather Testbed earlier this year. And Kevin Thiel wrote up some recommendations that he is still sort of in the review or draft phase of, but some thoughts that we wanted to share on paper as a result of what forecasters thought of during this experiment was that the applications for the GLM background imagery, as we've talked about, it's most useful to observe synoptic scale and some mesoscale features when ABI visible imagery are unavailable, but it doesn't have as fine a resolution as visible imagery. And as far as the GLM data quality product goes, it's very useful for identifying those subarray boundaries, changes in flash detection efficiency, and potentially questionable data when it comes to a lesser amount of flashes detected by the GLM. For training, familiarization with GLM subarray boundaries and their impacts on data quality and detection efficiency are absolutely crucial to understand how to apply the GLM data quality product. So the more we can get forecasters familiarized and used to and comfortable with this GLM data, especially understanding like where those subarray boundaries might be, the reasons for lower detection efficiencies, that's going to be really important for any training or further products that actually get implemented into operations concerning GLM data quality. For future research and development, we want to continue to explore more of those condensed display options like we were just looking at with the red detection efficiency and the pink data quality flags to really conserve screen space and make it as quick as possible that a forecaster or a meso analyst who's passing information onto a warning operator can maintain that operational situational awareness and keep all these things in mind as the forecast is issuing warnings or other products. Next slide. Okay, so to summarize and conclude here, the GLM background and data quality products offer insights into the flash detection efficiency and the limitations of some of the satellite-based lightning mappers. That background imagery can be a suitable stand-in for missing ABI visible imagery in determining synoptic scale features, or even the location of anvil plumes from ongoing convection. The GLM data quality product provides real-time estimates of detection efficiency and highlights possible degradations due to light saturation in individual pixels, especially along those subarray boundaries which stretch across the US. And different color maps and panel configurations can help synthesize all these data more efficiently, and more work is needed on this end. And then finally, adequate training will need to be developed to familiarize forecasters with the utility of these products. So I think that's all Eric and I have to say for today. And we want to thank you for attending, and we'll be happy to take any questions or discussion.
All right. Thank you so much, Joseph and Eric, for that excellent presentation. I know I learned a lot. Hopefully, most of us did as well. But before we start and moving on to our open discussion portion of this presentation, I'd like to encourage attendees to participate in the open discussion, particularly those from the weather forecast offices and regional headquarters. You can ask questions by typing them into the GoToMeeting in-call chat room. Looks like we've already had a few come in. Or you can ask them verbally as well, in which you may want to turn your camera on, and that would indicate to me that you would have a question to ask, and I can call upon you. You can think of turning your camera on as raising your hand, if you will. I'll encourage participants to turn on your camera when speaking, and for everyone to change their view setting within the GoToMeeting application from the default view to active cameras. And you can do this by navigating to the top center of the GoToMeeting application, selecting the drop-down menu from what probably says View Everyone, and then changing it to active cameras. Also, please share any feedback you have on the session or the Satellite Book Club in general by using the survey link that will be shared in the GoToMeeting in-call chat room shortly. You can also contact the Towers S team, Kashad Bowman and Emily Maddox, for questions about the Satellite Book Club or for configuration of satellite products as well. Looking ahead, in a week from today, on Thursday, July 18th at 12 p.m. Eastern Time, I'm going to try to not mispronounce his name, Stuti Deshpande from Towers S team will discuss enhancing data quality and maintenance in the ASOS SCPs. All right, so let's get on into the some questions. I think I'll go ahead and maybe look at these questions that are in the chat room first, and then Paul, I see you got your camera on, so we'll get back to you here shortly. We have some from Steve Goodman. He asked Joey, if AWIPS can make a mouse over storm object meteogram, do you think that could help make it easier to diagnose where the trends, for instance, increasing or intensifying, are not correctly represented in the GLM degradation areas? And should the user compare with the complementary ground-based lightning network depictions in AWIPS?
Yeah, Steve, that's a really great question. A lot of forecasters have been asking about that sort of storm tracking, the change in GLM values over time, because it's really those trends that we tell forecasters to look at, right? Especially in lower flash rate storms. The problem is it's really difficult to implement that tracking into AWIPS. I think it could make it easier to diagnose those trends if forecasters did have something like a storm tracking meteogram. And that could also, highlight those degradation areas if you see a drop in the GLM values. But for now, we've been training forecasters to kind of track those with your eye as you can as storms progress over time. That is some work that I've been working on, not necessarily making something that's implementing an AWIPS, but really tracking those storm feature change in the values of the gridded products, so FED, MFA, TOE. I did a presentation at the Satellite Book Club a couple months ago about tracking those values for a tornado outbreak earlier this year. And I'm also working on doing that same thing for a set of large hail cases from earlier this spring. So more on that coming later, I think. But yeah, forecasters would definitely like that. And as far as comparing with the ground-based networks, that is something that we always try to hit home with forecasters, is that the GLM is just one piece of the lightning puzzle, and you need the GLM, the ground-based networks. Maybe you can look at local lightning mapping array data if you're lucky enough to have one of the LMAs in your forecast area, as well as other observational data sets to really get the complete conceptual idea of thunderstorm development.
Awesome. Thank you, Joe. All right, Scott Lindstrom had a question about detection efficiency, comparing that from GOES 19 to GOES 16. Is there something different? Would there be a difference between different satellite platforms? And I think Steve Goodman actually had a comment on this particular. It said, Scott, the reduction of the GLM stray light and electronics tuning in the GOES 18 and 19 platforms are a few percent data efficiency, the DE improvement over 16 and 17. And I kind of have like maybe a follow-on question with that as well. Would the sub-array boundaries, would they change in location between platforms, or are they generally around the same?
Generally, they'll be in about the same locations. I think with a yaw flip, they might shift slightly, and then during the diurnal cycle, the exact position of any GLM sensor pixel does drift around in the field of view a little bit, and so they're generally stable in the same general vicinity, but they could move some.
Okay, thank you. Another question from Steve Millard. Do you ever see saturation happening at high solar zenith angles due to the three-dimensional effects like side illumination of clouds or like towering cumulus?
Eric, do you want to take that one?
Yeah, I mean, it's an excellent question. It's an excellent question in part because it's very much pointing out exactly how the detection principle works here that we're using. So I don't know that we have any specific examples of it. We just got it running in real time for the testbed this past May. So we don't have that giant case library that you might need to see some of those kinds of things. But if you ever did have a side illumination of a very bright cumulus turret, probably towards solar noon, that it could show up there as well.
Yeah, I just wanted to add that side illumination as a false lightning event is something that has been documented in the GLM before. So that's definitely possible.
Yeah.
Thank you. Paul, I will take your question if you have one.
Yeah. First of all, I'll just say, hey, I appreciate this information. I've always been fascinated by just the concept of GLM and how it's capable of detecting lightning flashes on the daylit side of the Earth. So I appreciate all this background info. Now I know and can explain to my crew here a little bit more about how that process works better. So I appreciate that background. So I have two questions. The first one's easy, so I'm just going to rattle off both questions at once, and you can respond to them. The first is simply, are we looking forward to this this information, these data detection efficiency and such, data quality? Are we looking forward to this in a future build of Tower S? And then the second question, so I'm in Montana, right? And you were talking about how detection efficiency is less than 40% across the West Coast when you're looking from goes east. So West Coast users are going to tend to look more at goes west. Well, in Montana, we're kind of right in that a sweet overlap spot where really the resolution from either view is about the same, and we do get a benefit from viewing both satellites and actually choosing a satellite based on parallax and things like that, which we have to be mindful of in our operations. But I'm a little concerned that even if I flip over to goes west, I'm still going to be in there at around that 40% detection efficiency. So would you agree with that? And yeah, I don't if you can add any comment on our situation here in Montana.
Joseph,
Eric,
do you want to I can take a whack at that. Yeah.
Okay, yeah.
You're exactly right, Paul. It's just a sort of characteristic of the instrument that in the northern Great Plains that you're at a lower detection efficiency from both points of view. One of the nice things about those synthesis products where we highlighted in red that lower detection efficiency is that was sort of done live in AWIPS in real time. It's not sort of part of the core product processing. And so it might be that at a high plains office, you might choose a different threshold there because you know that you're always sitting around that 50% mark. And so you want to sort of see if you're above or below that in your region. And that might be a good thing for us to keep in mind if we think about operational implementation to allow some knobs like that for individual offices to tailor to their situation. You also asked about operational implementation. We've designed this with the Tower S ISAT's processing system in mind. It was running in real time. So we're certainly pitching this as a thing that we could ship to the field, and it's one of the reasons why we wanted to present today is to get that in front of a wider audience. I think one of the things we took away from the test bed is that the restriction to 16 gray levels in the background image probably hurt its applicability, and that's really easily solved. So some tweaks might get made as well by the time we get to the end. And we also didn't show you, I don't think, the calibrated background images today, which also cleans up the appearance of those some. So a few improvements and tweaks, but we think we're pretty close to ready to go if if that's of interest to the Weather Service.
And I just wanted to add to what Eric said there. You may only be getting that estimated 40 or 50% detection efficiency from either the goes west or goes east GLM in your area in Montana, but that may not be the same 40 or 50% flashes, right? So, the subset of flashes that the goes east GLM is observing may be different from the subset of flashes that the goes west GLM is observing. So you mentioned already that you guys in your office, your personnel have that experience of trying to choose between the two satellites depending on what seems best for which operational setting and what your limitations are for that particular day. So we tell offices in that central high plains region, even further south into like Colorado, Kansas, New Mexico, if you're on that sort of edge between which one is more efficiently detecting the flashes, goes east or goes west, definitely best practice is to be comfortable loading both of them in. Sometimes it may be good to have both of them at the same time when you're making a warning decision. Some work is being done on a combined product that's sort of outside the scope of this presentation, but there may be a combined goes east, goes west, gridded product coming up the pipeline soon. And then one other thing I just wanted to reiterate is, of course, best practice is to incorporate that with the ground-based lightning detection networks. So all three of those things together, goes east, goes west, and the ground-based detection networks will give you that more complete picture of how the lightning is evolving in different thunderstorms.
All right, thank you, Paul, for those questions. Those are very good questions, similar to ones I also had. Well, I feel that might be the only time that we have, so we're gonna have to wrap it up. Thank you again to our presenters, and Jordan, we'll pass it to you.
All right. Well, thank you so much, Joseph and Eric, for that presentation. Really fascinating stuff. Look forward to seeing more from the GLM. Obviously, a useful tool here in the summertime. The Satellite Book Club continues every Thursday, and next Thursday at 12 noon Eastern Time, we're going to have our very own Studi Deshpande from the Tower S team is going to be discussing enhancing data quality and maintenance of the ASOS SCP. That's the satellite cloud product. So please tune in next week to hear a little bit more on that. In the meantime, if you have any questions for our Tower S team, we have Kashad and Emily standing by, or you can get in touch with us on the Tower S internal Slack channel. So many different ways to get in touch with the Tower S team if you need to. With that, we'll leave it there for this week. Stay cool, everybody, and hope to see you again next week. Take care, and thanks again.